A modern commercial project launches with meticulous blueprints and an agreed-upon delivery date. Yet, midway through execution, progress abruptly comes to a grinding halt, resulting in massive delays and budget overruns. The root of this failure often stems from a severe categorical error. Project teams treat scheduling and planning as the exact same thing. They are entirely different disciplines. Scheduling is a narrow, one-dimensional metric. It provides a simple timeline of when tasks should theoretically happen. Planning is the comprehensive pre-construction strategy required to execute that timeline. It dictates exactly what work occurs, who performs it, the specific materials and machinery required, and the physical constraints restricting the site. Relying strictly on a schedule assumes the job site operates in a frictionless vacuum. To actually build a structure successfully, teams must map the complex physical realities of the site long before execution begins. Modern construction planning is a massive, resource-constrained optimization problem. Resolving it requires calculating 5 distinct variables simultaneously: scope, time, resources, risk, and integration. Historically, large-scale projects fail because these 5 variables are handled by different stakeholders, operating in isolated software silos. The estimator works in one system, the scheduler in another, and the on-site manager in a third. We are going to construct a functional project plan from the ground up. We will start with a flat, theoretical timeline and progressively layer on the mathematical and physical constraints that govern a real build. By the end, we will see how engineering the operational reality computationally is the only way to control the chaos of a physical job site. The process begins with scope definition. Planners extract the raw geometry from architectural drawings and translate it into actionable labor. This 3D wireframe is a work breakdown structure. Breaking the scope into manageable units defines the tasks. As blocks drop into a 2D flowchart, they form a strict dependency network. The continuous red path highlights the critical path method, determining the minimum project duration. But CPM contains a fatal mathematical flaw. It is purely deterministic. The algorithm assumes infinite labor and machinery are available precisely when a task requires them. A CPM flowchart dictates the ideal sequence. Without factoring in the reality of physical limitations, it remains a theoretical wish. Real job sites have finite inputs: a fixed number of workers, limited machinery, and a restricted footprint. This Gantt timeline sits above a labor histogram. When concurrent tasks demand resources simultaneously, the histogram spikes past maximum capacity, creating a bottleneck. Through resource leveling, planners shift non-critical tasks horizontally, smoothing demand to remain safely below site limits. This constraint applies to spatial logistics as well. Planners map crane swing radiuses, delivery routes, and laydown areas to prevent overlap. Failing to solve resource constraints during the pre-construction phase guarantees on-site trade clashes, idle crews, and cascading delays. A leveled schedule still relies on a dangerous assumption that tasks take an exact, fixed amount of time. Weather systems, supply chain disruptions, and human error make construction inherently probabilistic. Modern planners abandon fixed durations, integrating risk assessment directly into a task to create a fluctuating probability cloud. Using Monte Carlo simulations, software runs thousands of randomized scenarios, settling into a heat map to find the exact mathematical probability of different outcomes. This transforms a rigid target date into a risk-informed schedule, complete with mathematically calculated contingencies. By modeling uncertainty directly into the timeline, planners prevent brittle schedules from shattering under the inevitable friction of the real world. Until recently, scope, resources, and risk were calculated in disparate software programs, requiring manual reconciliation. Collapsing the timeline, histogram, and probability map merges them into building information modeling, a unified database. Linking schedule to 3D geometry creates 4D planning. Tying in budget creates 5D. As this digital twin constructs, time and cost tickers advance in perfect synchronization. This yields precise automated quantity takeoffs, exact cash flow matching, and digitally resolves physical pipe clashes. Multi-dimensional digital integration allows teams to fully construct the building in data. They absorb their most expensive mistakes in a simulation rather than on the job site. Even a perfect 5D model must survive contact with daily execution. Once ground is broken, pre-construction ends, and the plan must adapt to live data. Teams utilize lean construction principles on site, focusing heavily on stabilizing daily workflows, eliminating material waste, and ensuring highly reliable handoffs between trades. On this dashboard, emerging AI and advanced analytics track that daily progress. As the supply chain alert drops in, the AI dynamically reroutes the critical path and resource allocations to absorb the shock in real time. Machine learning models analyze vast sets of past project data to predict where bottlenecks will occur, allowing managers to allocate extra labor before a delay even materializes. Through lean tools and AI analytics, the modern construction plan ceases to be a static document. It functions as an agile, adaptive central nervous system for the entire project. A rigorous project plan links scope, time, resources, risk, and cost into a single computational framework. Empirical data across the industry shows that early, exhaustive front-end planning is the single strongest correlate to a project delivering on time and under budget. Scheduling is drawing sequential lines on a calendar. Planning is the rigorous design of project physics. The true purpose of construction planning is not predicting the future with absolute certainty. It is engineering a resilient system capable of surviving it.